Hello everyone. Welcome to the presentation of the paper entitled Robust Super Resolution of Real Faces Using Smooth Features, which is a joint work by Saurabh Goswami, Akanksha, and Dr. Rajagopalan. I'm Saurabh Goswami, an MS student from Indian Institute of Technology, Madras. The task of super resolution is to generate a high resolution image from its low resolution counterpart. There are two approaches to do this: paired superresolution, where pairs of high and low resolution samples are available, and unpaired superresolution, when no paired data is available. Paired superresolution networks, which can be trained with phase-specific priors or without, produce great results on bicubically downsampled images. However, for real degraded facial images, they fail to produce sharp, high-resolution outputs. Unpaired superresolution methods often use generative adversarial networks to model real degradation from an appropriate dataset, and use the synthetically degraded images to train a superresolution network. So, these methods are better equipped at handling real degradations. However, for differently degraded versions of the same image, they fail to maintain a consistent output. We attempt to address both these shortcomings by training a super-resolution network which is robust to real degradations and which produces consistent output for different degradations. From this point onwards, we will refer to bicubically downsampled images as clean images and real degraded images as simply degraded images. To make our network immune to real degradations, we train a GAN to realistically degrade clean bicubically downsampled low-resolution images. Depending on a random vector, it can produce differently degraded versions of the same input. Our main network consists of two modules: a feature extractor that extracts the feature volume from an input low-resolution image, and a super-resolution module that generates high-resolution image from that feature volume. During training, we first obtain a convex combination of a clean low-resolution image and one of its degraded counterparts. This interpolation operation is performed so that the input to the network during training contains enough degradation and at the same time enough details for reconstruction. To train the network for super resolution, we put the combination image through the network and do a backpropagation based on the loss function shown on the screen. It's a combination of pixel-wise loss, perceptual loss, and adversarial loss. To incorporate consistency across different degradations, we put the clean image, degraded image, and combination image through the feature extractor and minimize their pairwise sync-on distance. This ensures that the feature extractor will maintain a smoothness as we gradually move from a clean image to one of its degraded counterparts, keeping the variation in the super resolution output to a minimum. The smoother the features are, the more consistent the output will be. To understand the significance of alpha, let's gradually move from a degraded to clean version of an image. As shown in the figure, alpha equal to 0 attains the smoothest transition, hence robustness, and alpha equal to 1 attains the most faithfulness. In our experiments, we notice that alpha equal to 0.3 attains the best trade-off between robustness and faithfulness, and hence we use this value in our training. We show more examples of this in our supplementary material. During testing, we put a low-resolution image through the feature extractor and feed the features to a super-resolution module to get the output. When applied on differently degraded versions of the same image, our network achieves the most steady output. Note that the low-resolution images here are extremely degraded, but still our network maintains a consistent output for all of them. This test is extremely important for evaluating the effectiveness of our network. We also perform smoothness tests to see how the output changes as we gradually move from clean to degraded versions of an image. In this test, we combine clean and degraded versions of the same image using gradually increasing alphas. Being trained on one alpha, how it generalizes to other alphas will tell us how smooth our feature extractor is. Note that our method achieves the smoothest transition. For an objective evaluation, we tested our network on both bicubic downsampled and real degraded images, and it performs very close to a state-of-the-art unpaired super-resolution network in terms of PSNR and FID. In conclusion, we trained a robust super-resolution network that leverages smoothness of features to maintain a consistent output for a variety of different real degradations, and we experimentally show the trade-off between robustness and faithfulness and achieve a good balance using interpolation. These are some of our references. Thank you for joining us.